Thank you. All right, John, you got a mic or you need this one?
Welcome to our new 2022-23 annual speaker series. Tonight, our speaker is Dr. Eric Perlman, who is a professor of aerospace, physics, and space sciences at Florida Tech. Dr. Perlman received his AB in physics from Occidental College and his PhD in astrophysics from the University of Colorado in Boulder. He moved to Florida Tech in 2007 after postdoctoral fellowships at the Goddard Space Flight Center and the Space Telescope Science Institute, as well as research and staff and faculty positions at Johns Hopkins University and the University of Maryland. Dr. Perlman is an observational astrophysicist whose research concentrates on the nuclei of galaxies, their physics and evolution, particularly those in which the central black hole has a large rate of accretion and is abnormally active, the so-called active galactic nuclei. He has strong interest in clusters of galaxies, galactic activity in clusters, and observational cosmology. Dr. Perlman's talk tonight is entitled Black Holes, Nature's Hearts of Darkness. Please join me in welcoming Dr. Perlman.
So thank you, everybody. Let me share my screen.
Okay.
And thank you very much for that nice introduction. Let me see here. Let's see. Is it going? Hold on. I have to do some permissions here on my end. This is what happens when you get a this is what happens when you get a new laptop. Okay. Okay. So let's try sharing again. All right, there we go. Can everybody see my screen?
Yes.
Okay, great. And if I do that, does everybody see the whole screen first, all full screen, or does everybody see the film strip at the bottom?
We see the film strip.
Okay, let's not do it that way then. Let's do it full screen. Let's do it that way. Oh.
We see
There we
it.
go. Yeah, but I'm getting distracted by the closed captioning. Okay, so let me tell you the reason why I put this talk together. The reason why I put this talk together is because there's a lot of really exciting things going on around black holes. And excuse me? Excuse me? All right, anyway, there are a lot of interesting things going on around black holes, and a lot of it has been basically stimulated by some very new findings, basically very new meaning in the last 5 years. And so we're going to be talking about basically two sets of results. One of these sets of results is from the Event Horizon Telescope, which, as you'll see, is an array of radio telescopes. And this is the array that announced the discovery of the photon ring from the black hole of the galaxy M87, which is going to be one of the things that we talk about. The other one is all of the results that came out from the Keck telescopes and also from the VLT, and specifically an instrument on the VLT called gravity. And basically what I'm going to do is I am going to be combining all of this stuff into a talk. Some of it is going to get a little bit technical because some of it will talk about some of the nitty-gritty things, not only about the array, but about why certain things were done. In other words, why it is that certain results took time to be released, why M87 was released before Sagittarius A star, the center of our galaxy. It's an interesting view into, you know, things like really understanding your images and your data, which I know people like you, being amateur astronomers, and, you know, in many cases, many of you have good telescopes and setups yourself. You appreciate things like this. And so I'm going to go into some of this in some detail. So, okay, that is one of those that doesn't play. That's what I thought. All right, so why black holes? So black holes are objects that are so massive and so dense that their gravity basically cuts them off from the whole universe. They are very small. They are very dense. So if you were to have a black hole that was the mass of our sun, so our sun suddenly collapses and becomes a black hole, it would go from the size that it currently is to being 3 kilometers in size, not very large. It would also have an escape velocity that would be the speed of light. So nothing could get out because nothing can travel faster than the speed of light. We actually see these things in the universe. We see them at stellar masses. And of course, many of you have probably heard about the results in the last 5 or 6 years from LIGO in gravitational waves, where we've seen a lot of these stellar mass black holes, as well as the supermassive variety that I'm going to be talking about today. And they also tend to be the prime mover for various high energy active phenomena in the regions around the black hole. Light near a black hole gets very strongly bent. And the reason it gets very strongly bent, as you can see in the illustration that is on the right-hand side of the image, is that you have this huge distortion of space and time that goes on. And so, you know, gravity bends light because light travels along the shortest path between any 2 points. But if the shortest path between any 2 points is a path that goes up and down a gravitational well to somebody outside of that black hole, it's going to appear curved. And so the result are paths like what you see here. This is something that we're going to refer to later on. Things that are star mass in size basically get to be black holes as a result of supernovae. Okay. But things that are in galaxies are a different matter. These are the densest parts of galaxies, and we believe that the black holes may have formed as part of the galaxy formation process. That's kind of beyond the scope of this talk. But what I do want to talk about, which is going to be relevant, is that when we talk about a galaxy's black hole, any black hole really, there's a few important radii that we have to talk about. So black hole physics is something that is completely specified by just a few things: mass, spin, and charge. We think the charge is likely to be 0. But the mass and the spin are interesting quantities. If you have no spin, then the most important thing is this event horizon at this radius of 2gm/c², which is this 3-kilometer radius for a 1 solar mass black hole, or for a black hole that is the size of some of the ones that we're going to be talking about today, it's AU in size. For one that is 10 to the 8th solar masses, it is 2 AU. So that's a nice, useful number to keep in your head. Matter orbits in a stable way around black holes until you get to this point called the innermost stable central orbit, or ISCO, which is at 6 gm/c². So that's 3 times the Schwarzschild radius. So outside of that point, matter can orbit indefinitely in circular orbits. But inside that radius, there is no such thing as a stable orbit. All of the orbits are unstable, and matter spirals rapidly inwards. So matter that is at the ISCO also sets a minimum orbital period. This minimum orbital period is going to become very important, okay? So this is what's given by this equation at the near the bottom. For a 1 solar mass black hole, this is about half a millisecond. For a 10 to the 8 solar mass black hole, it's 12 hours. Remember that number later on. So what happens to light near a black hole? Light gets severely deflected by the gravity of a black hole. And the closer you get to the black hole, the larger the amount of deflection. There is a radius at 1.5 times the Schwarzschild radius where light goes around in a circular orbit. So a light ray that is emitted tangentially to the horizon at that at a distance any smaller than that gets captured. And you can see this in the illustration here. If it wants to escape, it's got to be emitted at an angle of less than 180 degrees. And as the radius is actually decreased from that 1.5 Schwarzschild radius to the Schwarzschild radius, the range of angles from which light can escape goes down from 180 degrees to 0. And at the horizon, it's 0 and light can't escape anymore. All right, that's what I want. So you have a structure that looks like that. You have the event horizon here at the Schwarzschild radius. You have the photon sphere here at about 1.5 times the Schwarzschild radius. Okay, and so this defines where the photon ring that we're going to talk about later on is. Okay. Now, how do you see a black hole? The answer is that you don't unless there is some help. And what helps is if there is matter streaming in. Okay, this illustration is an artist's conception of material streaming in to a black hole. This material is being followed by the green arrows. As it streams in, it converts potential energy into kinetic energy. This kinetic energy gets converted into luminosity, basically what we see as light. And that's how you see a black hole. Now, black holes can be spinning. If they spin, what happens is that this innermost stable orbit can either move inward or outward, depending on whether the rotation is in a retrograde fashion. If it's in a retrograde fashion, the disk of matter that's accreting in is orbiting in the opposite direction from the black hole's spin. And in that case, the innermost stable orbit actually goes out. But if, on the other hand, they're both going in the same direction, which is what we call prograde rotation at the bottom, then the innermost stable central orbit, the ISCO, moves inwards. All right, so general relativity predicts a circular shadow, okay, around a black hole. This is the photon ring or photon sphere that I've been telling you about. However, that photon can be squashed along either the vertical or the horizontal axis. And we want to image the event horizon of black holes, not only to see if the black holes are actually there, measure their mass, but also to tell whether they're spinning. So that spin can affect how squashed the black hole is. But we also want to image it to see if we can tell whether our ideas about space and time are correct. I actually won't have too much to say about that because the work is still continuing on that. So let me introduce you to the Event Horizon Telescope. Okay. So the Event Horizon Telescope is an array of radio telescopes at a wide variety of places around the Earth. Most of the telescopes here are shown. The only ones that are not shown here are, number one, a telescope on Greenland, roughly where my pointer is here. And then another one down at the South Pole, which is not shown here. The Greenland telescope is important for the M87 observations. And the South Pole telescope is actually quite important for the Sagittarius A star observations. And here's a larger view, and now you can see the Greenland telescope and the South Pole telescope. Okay, the reason those telescopes are important is because they represent the longest baselines, and so they also represent the best angular resolution. So the EHT observes at millimeter waves. Okay, so what you mostly do here is in the optical, right? Radio and millimeter is at much longer wavelengths. And of course, the shorter the wavelength, the better your resolution can be if you don't have to worry about seeing. And if you have an array of telescopes like this, you can combine the signals interferometrically and you can get superb angular resolution. And that's what's done here. Now, I want to call your attention to the bottom plot. And the bottom plot shows you that the millimeter wavelength range is not an easy one to observe in. Okay, you have all of these absorbing molecules like carbon dioxide, water vapor, oxygen, and ozone. And so what's in the atmosphere on a given night, particularly water vapor, can actually affect how good the atmosphere is to observe in quite a bit. And this is a zoom up actually on the range of the spectrum, where the EHT observes. The EHT observes right around 1 millimeter, okay, which is where this vertical line here is. And you can see that it's not a great part of the spectrum, and there's quite a bit of variation in how clear the sky, how much the atmosphere transmits, depending on what the amount of water vapor is in the atmosphere. All right, I am going to skip the recording telescope, and I'm going to basically mention that special relativity is important. Special relativity is important because of a couple of things that you see. One in particular, this thing called relativistic beaming. What relativistic beaming does is that it means that stuff that is moving at nearly the speed of light is going to emit light that is actually thrown forward in its direction of motion from our perspective. And so it's going to be brighter in the direction that it's moving towards. This is actually important in what we see in the EHT images. All right, so let's skip to this. Some very quick questions and answers. First of all, how big are the Schwarzschild radii? So the numbers that you see on your screen use the best case masses for both Sagittarius A star and M87. So for Sagittarius A star, the mass is about 4 times 10 to the 6, 4 million solar masses. So the Schwarzschild radius is 1.27 times 10 to the 7 kilometers, or about 0.08 AU, or 10.5 micro arc seconds. For M87, which is a much bigger black hole, it's 6.5 times 10 to the 9 solar masses. Its Schwarzschild radius is almost 2 times 10 to the 10 kilometers, or about 130 AU. So that means its black hole has an event horizon larger than the solar system. So the photon ring should be about 5 times the Schwarzschild radius. Where does that come from? So this is the diameter, and that basically takes the middle of that 1 to 1.5 times the Schwarzschild radius. We're measuring the diameter, so you multiply that by 2. Okay, and then you get another factor of 2 because you're looking at the inner part of the ring. Okay. So these were not the first observations in the millimeter. This was actually done by the GMVA, which started about 10, 15 years ago. It started observations, actually not 6 years ago. That was written in 2018. So now it's more like 10 years ago at 1.3 millimeters. But the big advances were several things. Number one, better control of weather. Also, arrays at ALMA and in the South Pole, which had much lower precipitable water vapor. They also got hydrogen maser clocks at all of the telescopes, which enabled them to measure the time better. And also they greatly increased the data rate. Now, the more telescopes, the more baselines that you can have. This made a big impact. So what you're seeing on the right here is the telescopes that they had prior to the building of ALMA and the South Pole telescopes. And what you're seeing on the right now is what they have, particularly for M87. This was from one of the papers where the discovery was announced. So you can see that there are just a lot more baselines. The more baselines, the better your sensitivity. And so the earlier observations basically found only a jet and a core that had a size that was consistent with the innermost accreting material, but we didn't know if it actually contained a photon ring because it didn't have the angular resolution. Okay. All right, so this is what those previous images showed. So here is the M87 jet, and you can see this jet of material that appears. That jet is seen at about a viewing angle of about 17 degrees. And the smallest thing that you can see on this image is about 30 times the Schwarzschild radius in size. And as you go up in frequency, you get to smaller and smaller angular resolution, better and better angular resolutions. These data points on the bottom show you the size of the cores that had been measured. And as you can see, they went right down to the innermost stable central orbit with the observations that existed before the EHT. All right. Now, Sagittarius A star, why do we think it's a black hole? We think it's a black hole because of data like these. This is a compilation of about 20 years worth of data from the Keck and UCLA Galactic Center group. These are real data, and what you're looking at, and I'll start it again, is that you are looking at stars moving around the black hole that's at the center of our galaxy. They are orbiting a dark, unseen mass that's at the position of the star there. And in some cases, we see a complete orbit like this star SO2. From that, we can determine how much mass there is. And that mass appears to be, like I said, about 4 million solar masses. We also know that there is a black hole from the observation of variability in the infrared and the X-rays, such as the images that you see there. So these are images that were taken in one night. And you can see that there is something flickering near the center of that image. What is flickering is the material right around where Sagittarius A star is. And at the bottom right, you can see how that object varies. On the top, you can see the variations in X-ray as observed with the Chandra and XMM Newton telescopes. And on the bottom, you can see the variations in the near infrared as observed with the VLT with NACO and NIRCam 2. You can see that they vary on very short time scales, as short as a few minutes. And the standard argument that you make is that, well, nothing can travel faster than the speed of light. And so if you have a variability time scale of such and such an amount, then that means an image, a region that is no longer than the speed of light times that. And so how fast the flares were basically means that, so quick math, Who knows how long it takes for light to travel from the Earth to the sun? Does anybody know that number? So I'll give you that number to
Yeah, the
compare.
consensus here is 8 minutes.
That's correct. I was gonna say that. It's 8.3 minutes. And so if you compare that to some of what you're seeing here, okay, so you're seeing in the two in the two flares that you see on the right, you're seeing variability on timescales as small as about 20 minutes or so. So that is a small fraction of an AGN. That would be of an AU, right? So eight minutes would be 1 AU. This would be like 3 AUs, but that also means that remember the Schwarzschild radius of M87 is 0.08 AU. So we're actually going fairly close to the black hole, not quite down to the innermost stable orbit, but not that far away either. In fact, where we're going is right here, this shaded region, okay? So the X-ray emission region gets you to this shaded region, and the data from S2, the orbit gets you to 10 to the 3, but then the fact that it is smaller and the fact that it doesn't move gets you much closer, basically the same amount. All right, so in 2017 and 2018, this star called S2 made its closest approach to the black hole. And it got actually very close. It got about 120 AU from the black hole. So that's roughly 3-4 times the distance that Neptune orbits our sun at. And they were able to do some really nice observations, this being the VLT with the gravity instrument, where they observed the motion of the star around the black hole. Some of those observations are seen at the bottom here. So you can see Sagittarius A star and S2 in its path around the black hole. You can see, where it got to its closest point in May and June 2018, where it got to about 100 AU, as well as some of the further out observations. So this plot shows the complete orbit. Those observations were right here in time on the lower left. So if you can see my cursor, I'm circling them. Okay. And what you can do is you can compute the velocities that you observe, okay, at all of these different observations. So all the observations that they've done, they're shown on this plot here. This is a zoom up of this region here, and the velocities that they got are right here. Notice that they go up to about 4,000 or 5,000 kilometers per second. This is actually not a very large fraction of the speed of light, but it's an appreciable enough fraction that they can actually begin to test what special and general relativity does. And the answer is it passed. But they also did something really interesting. So during these observations, it turns out that the emission varied. So these are some of those observations, May 27th on the bottom at the left and July 22nd. And you can see these small variations that they observed on time scales of 10 minutes or so. the period that they got was about 50, 60 minutes in both cases. And in fact, the angle of polarization moved around in basically a circular fashion. And what also moved around was the position of the central source. And it also moved around in about a 60 or so minute period. And this was fitted by something that had a radius of about 7 times the Schwarzschild radius. And it basically fits with matter that's orbiting at that radius, which is kind of neat. We're seeing matter that is orbiting right close in to the Schwarzschild radius of this black hole. This is something that had never been seen before. How close in are we going? So these are the 3 points where they saw the variability and that circular motion. Right here, this red point is where that innermost stable orbit is, basically really, really close to where the black hole's innermost stable central orbit is. All right, so Sagittarius A star is at the center of our galaxy. And it is actually the one that is slightly larger on the sky. So why didn't they release it first? So this slide is actually wrong. They're not working on it anymore. It got released about a year ago. But there's several reasons. First of all, there's lots of dust. So between us and Sagittarius A star, there are about 30 magnitudes of extinction in the optical. So we only get 1 photon in 10 to the 12. Now, dust normally doesn't have an effect in the radio. But with Sagittarius A star, you're observing at a very short wavelength, only about 1 millimeter. So a couple of things are very important. One is scatter broadening, and the other one is scintillation, and they are both caused by all of the dust that you can see in this image, and the galactic center is right here. And this is an image that was taken in the infrared. So scatter broadening predicts that the source radius is actually proportional to 1 over the wavelength squared. If it dominates, you don't see the ring. You actually need 2 frequencies so that you can rule out scatter broadening, so you don't see this 1 over wavelength squared dependency. What's more important is the fact that the black hole is much less massive. It's about 1,500 times less massive. And so remember we talked about orbital timescales. So light travels around the photon orbit of M87 in 7 days. What that means is in a 1-day observation, things are pretty stable. Across the Schwarzschild radius is about 18 hours. Still not bad for a 1-night observation. Now let's go to Sagittarius A star. The black hole is 1,500 times less massive. That means that the travel time around the photon orbit is about 6 minutes. And across the Schwarzschild radius, the light travel time is about 40 seconds. That's trouble, because what that means is that things can change very fast, given what we've already seen. We already saw that we had infrared variability. There might be radio variability. What you're looking at the right is 3 snapshots of the accretion flow at different times during a simulated 12-hour observation. And the bottom part is 4 snapshots at different times during the night. You can see these don't look very much alike. This is the problem with Sagittarius A star. They had to figure out how to use data where things were changing on timescales of minutes. It's not easy. Okay? Even with M87, things changed, but fortunately, they didn't change on daytime scales. What you're looking at here were some of the visibility data. I don't expect you to understand that too much, but the minima turn out to be quite important. They tell you what the size of the ring is. And so that turns out to be quite important. The green points show you what the models that they look at to actually figure out the image and what it looks like. This is what some of those variations can produce if you have flickering. And now you can see why this produces such a problem. All right, so here's what those data actually looked like. So this is one night worth of observations for Sagittarius A star. And the critical plot is this plot at the bottom. So you can see the time in hours, and you can see the flux density that was observed at ALMA and the South Millimeter Array. And you can see that it was changing on time scales as small as a few minutes. And you can see that it actually looked different at the ALMA than it did at the submillimeter array on Hawaii, and it also looked different at the South Pole Telescope. That's part of the problem. They had to understand that. All right, so M87 got released first. This is the optical image of M87. These are its radio lobes, and here was the image. And you can see the ring. You can also see that one side is brightened. Why would one side be brightened? It's because you're looking at stuff that's orbiting the black hole, and where it gets brightened, this is the part of the disk where the orbit is closest to our line of sight, and so it's brightened by relativistic beaming. Okay, just to place it in context, the image on the left is a Hubble image. It's rotated, so don't pay attention to the angle. The image on the right is a set of images with the Chandra X-ray telescope. So there you can see the jet, that jet. So yes, they are, both the optical and the X-ray and the radio jet are at the same direction. That jet was the inner part of what the inner part of that was what you were seeing in the earlier millimeter wave images. All right, so here's your image. Okay, here's your image, and they responded to all those challenges, as I said, with extensive retrofitting of the telescopes, real-time control of weather. What that means is that they only allowed each telescope to observe when its weather was good. This meant they only got the best data, but there was still some effect from turbulence. The way you can tell that there was some effect by turbulence is by comparing the data on successive nights. So here you have April 5th, April 6th, April 10th, and April 11th. And you'll notice that the image changes just a little bit from night to night. Okay. They also did lots of new imaging techniques. They did 4 double-blind teams modeling the data everyone seemed to get the same results. This really increases your confidence in the results. They also did extensive simulations to understand whether you could get other structures like a disk, a double source, a jet, and each of those were rejected. But the photon ring that is predicted plus magnetohydrodynamics does fit the data. So some of these simulations are what you see at the top, and the bottom panels are the key points. What they do is they check the predictions of those against the data, and what you can see is that the disk and the double models do not fit the data at all. A crescent partially fits it, but not great. The ring is clearly the best fit. Now, we need to do more work on this. We see the ring, we see the shadow of the event horizon. That's the dark part in the center. It needs to be confirmed by further observations, but it is the first time we've directly observed the photon orbit and the black hole itself. They did a lot of comparing to different accretion flow simulations. The idea was to try to figure out what kind of an accretion flow it was. And so we'll talk a little bit about that. The mass that they got was the 6.5 times 10 to the 9 solar masses. They measured it directly with the size of the photon ring. It turned out to be consistent with the measurements from stellar dynamics, but not with the measurements from gas dynamics. That's an interesting inside baseball story, which we can talk about if some of you like. The size, the circularity, the contrast, and the asymmetry are all consistent with strongly lensed emission from the vicinity of a black hole. They also indicate that the black hole has to be spinning and has to be spinning clockwise. And the way that they get that is, as you can see by the illustrations at the top, different rates of spin and different different rates of spin and different directions of spin mean that the black hole shadow and its photon ring would be squashed in different directions. And so what we see actually places a limit on that, but it's not that great. So the better our data gets, the more we will pin that down. All right, so now what you are looking at is something that was released just early last year, and that is the image of Sagittarius A star. And I think what I want to point out is that it looks pretty similar to M87. And the fact that it looks so similar to M87 is pretty remarkable. And the reason why it's so remarkable is because Sagittarius A star is a black hole that is 1,500 times less massive, but it is also a black hole that is 2,000 times nearer, right? Because Sagittarius A star is at 25,000 light years, whereas M87 is at 50 million light years. It's also pretty remarkable because it means that they solved all of those challenges that we were talking about, and in particular, the fact that the variability was on minute time scales, and so it made the data so hard to understand. They actually managed to deal with that. So, the asymmetry. So I mentioned that the asymmetry is actually something that is the result of relativistic beaming. So some of the material is orbiting the black hole, other material is in the funnel wall of the jet. The jet is nearly along our line of sight. So that material is moving at nearly the speed of light. So it's brightened by what we call Doppler boosting. One of the things that's being worked on now is the comparison of the data with jet generation models. Some of that involve the polarization results that I'm going to show you in a minute. A lot is still up in the air, but some of those results are very promising. Now, with Sagittarius A star, they got a mass that was consistent with what they thought before, but they also found that the black hole had to be spinning, and they found an inclination of 50 degrees or less. I just remarked about how similar it was. The spin is in the same direction as the accretion disk. That turns out to be roughly the same direction that the Milky Way spins. The substructure in the ring is actually real. So what do I mean by that substructure? I mean these bright spots. Okay, so that is real stuff. Whoops. That is real stuff. And it survives all of the various model fits. And it seems to point to substructure in in that ring, plus some relativistic beaming. But it's different from M87 because Sagittarius A star does not have a jet like M87 does. All right, so I mentioned jet models. So what you're looking at now is the observations in polarized light, which is something that EHT gives you for free. This is M87 again. And what you're looking at is the directions of the magnetic fields in the inner regions of the accretion disk of M87. And what I want to call to your attention is the fact that they are swirling. This is something that is very consistent with simulations and jet formation models that predict that the jet is formed by material that gets picked up by a coupling of the magnetic field with the spin of the black hole. It picks up material from the innermost part of the accretion disk. The accretion disk becomes broader. It spirals out into the polar regions and gets accelerated out into the jet by the magnetic field. So the fact that the magnetic fields look like this actually means something to people like me. And I specifically work on these jets, so I was really gratified to see a magnetic field that looked like that. There have been lots of simulations done, and what they're looking for now, so there are additional observations that are going on now. What you're looking at is a simulation, and they're looking for emission that looks like this. Basically, this would be stuff that is fainter, and they're looking for it in the low signal to noise stuff that is sort of in the noise, they're looking for it because it might be the material that gets accelerated up into the jet. All right, here's just some context. So this is all of the observations of the jet put into context. So you have the radio observations here on the left. You have HST and X-ray observations, as well as gamma ray observations here on the right. It's just a nice little illustration. Here's another set of simulated images. This is that stuff that they're now looking for, okay? This stuff that I'm circling. They haven't found it yet, but this is what they are looking for. All right. So, paradoxically, the matter that is generating the photon ring emission is not at the photon ring. It is actually outside the photon ring. You have to do extensive simulations with general relativity and magnetohydrodynamics to figure out where it is. And the reason why we see the light in a vastly different place is because of gravitational lensing. In other words, the bending of space-time. There are a variety of simulations. Some of the models have the material along the axis, some in the perpendicular direction, some along the walls of the jet counterjet outflow. Which is correct? The answer is probably all of the above. And the reason why is because we can't tell the difference between different models without a lot more work. Because the light paths that are near the photon ring are really, really complex. Individual solutions aren't unique. Okay, so that's why you get things like what you see at the right, where you have all of these different models that predict different geometries. They don't conflict with each other. We can't discriminate between the two, the different solutions. And so we just need a lot more work. Okay, let me skip to the last thing as far as interpretation, which is the fact that they did simultaneous observations with Chandra and New Star. And they basically allowed us to make the best constraint of what we can call the accretion rate, which is basically how fast matter goes in to that black hole. And M87 is actually not a very highly active galaxy. It's only accreting matter at 1/100,000th of what we call the Eddington rate, which is where light pressure causes the black hole to no longer accrete. So there are some things that we don't see. What we don't see are things that we would need additional theories, things other than classical general relativity to predict. Things like, for example, effects due to quantum gravity, or wormholes, or naked singularities, or additional fields. We don't observe any of those. All right. Now, if we had a lot better resolution, what kinds of things would we see? This is what we should see if we had really good time resolution and if we had fantastic data resolution, angular resolution. What you're looking at is you're looking at the image of the black hole moving around at a variety of inclinations. This is a simulation that was done by a team at the Goddard Space Flight Center, led by Jeremy Schnittman. And you can see a variety of things. You can see material moving around the black hole. This distortion that you see is a product of the distortion of space-time around the black hole. And you can see, you know, a number of you who have good memories will remember that something like this was part of what was shown in the movie Interstellar. This is actually what we hope to be able to observe in the relatively near future with telescopes like the EHT. It's not so far away. It's going to take a lot more work, but this is the kind of stuff that we want to observe. I am going to stop here and open myself up for questions. I realize I've gone a little bit long, but thank you very much for your attention. And I'm going to open myself up for questions. So thank you very much.
Thank you. I got the mic on now. All right. Any questions?
I'll ask one if no one else is ready. It's actually kind of two, and this last image helped a lot. All of the discussions of black holes seem to occur in two dimensions. The images you see, the drawings that people have. It's very difficult to understand what the three-dimensional implications are, and in particular, what our own perspective is. Like, where are we in this? That's a very good, in this motion that's occurring now. How do we see these two black holes, which are spinning? And the second part of this is, if the black hole wasn't spinning, and I don't know if we think any of those exist, how does that change all of this? Is there a photon sphere then that occurs around the whole ring? You know, the whole sphere? What would it be like? What would we see if it was not spinning?
Okay. Yeah, those are two great questions. I'm going to take the second one first. If we had a black hole that was not spinning, yes, we would still see a photon ring. What would be a little bit different is how much it would be squashed and in what direction it would be squashed. Okay. And the reason it would be a little bit different is because when a black hole is spinning, the shape of the ergosphere, the shape of the event horizon and the black hole itself actually changes. And so it becomes squashed in the polar direction and larger in the direction of spin. And so that affects the shape of the photon orbit. And so, yeah, that is why the shape of the ring is actually important to understanding whether the black hole is spinning or not. Now, the question of whether we think that there are any black holes that don't spin, that's a really interesting question. And so we don't know. It is so interesting because it tells us something about how the black hole formed and also how it may have grown. So any spin that the black hole has is a relic of two things. Number one, how it formed. Okay, so a black hole forms from some material, right? Conservation of angular momentum tells us that the more that the black hole, the more that the material gets smaller and smaller and becomes a black hole, the faster it spins. And so it has spin only because the material it formed from had spin. Now, how would a black hole spin faster or spin slower? It would spin faster or spin slower if you had one black hole eat another. So if you have two galaxies merge, then the black holes that are at their centers can also merge. If that happens, if you have two black holes that merge with each other, the spin can change, because depending on whether the spin's in the same direction or in the opposite direction, the black hole will either spin faster or slower. All right, so the first question had to do with that three-dimensional geometry. And I'm taking that question last because it's a really tough question to tackle. And I'm sorry, my other computer is doing this weird beeping. But the reason why it's so difficult is because of the bending of light and space-time that the black hole does. As you said, it really makes it difficult to understand the three-dimensional geometry that we see, because what we see is a two-dimensional projection. And so it's really, really hard to understand what that translates to in 3 dimensions without a lot of work. And this is particularly the case because of the fact that space-time is so bent. And so, you know, to take a look at the image that I'm presenting, what you're looking at, that stuff that is actually appearing above the shadow, that's actually coming from the material that is orbiting the black hole, but it is in the back, and its paths are being bent due to general relativity. And that's something that you can see if I put the simulation into motion, and as they move around the view, which you'll see in a moment, you can see that's this material up here. Okay. So yeah, it's really difficult to visualize.
The actual accretion disk, though, is a thin disk.
In most of these simulations that we've been looking at, yes. If you have a strong magnetic field, and if you have a spinning magnetic field, then some of that material that is close to the disk gets swept up into the magnetic field, and it goes to higher latitude. This is the material that becomes the jet, but what it does is that it puffs up the disk at the innermost part.
But I guess what I was leading up to, that the outer area is a disk. When we look at Sagittarius A star, what is that disk's orientation to us?
So we think yeah, that's a good question. We think it is something in the neighborhood of 30 to 50 degrees. We can't do better than that. It can't be larger than about 50 degrees because the amount of squashing would be too much. It can't be much less than 30 degrees though, because it's pretty symmetric. So that's about as good as we can get right now. With M87, it's a little bit different because M87, we're looking at the the jet fairly close to our line of sight, about 17 degrees. That jet is perpendicular to the disk. And so that means that the disk is at a pretty small angle, right? It's basically almost face on.
Right. Thank you.
Yeah.
Basically, I had the same question. So, is it correct that there's only two accretion
question.
disks?
Can you hear me?
Are there only two
Stop,
accretion
because
disks?
you're echoing.
No, are M87
Seem like
and Sagittarius A
that's the
star?
black hole that doesn't get captured.
Thomas,
Because
someone
it's
is asking,
gravitationally lensed.
Thomas,
The
someone else is
wavelength
asking,
coming in.
Hold on. There are two people asking questions. Please, only one at a time.
Yeah, can I ask the question? So, is it correct that there are only two accretion disks that have been imaged so far? Sagittarius A star and M87
There have only been two that have been resolved. And I
resolved.
think
Okay,
that
yeah.
is actually an important distinction, because there are more that have been imaged. They just can't be resolved.
Okay.
There are an additional set of papers from the EHT collaboration on other sources. In all of those, the accretion disk, the core cannot be resolved. You can measure a size, but that is about it.
Okay. And then going back to the first question. So looking at M87, we're essentially almost looking straight down on it, right?
Pretty
And
much.
with Sagittarius A star, it is at maybe a more inclined angle, but it's still it's certainly not nowhere near edge on, right? And
That's correct. Yeah.
right. And so there's just not enough. I mean, so when we find ones in the future, because I understand that most galaxies are supposed to have black holes in their middle. So were we able to see, black holes at will in any galaxies, their orientation would be all over the place, wouldn't it?
Oh yeah, absolutely. And so, we're observing two. These are what we think the orientations are. When we get higher resolution, so two things will give us higher resolution. Number one, observing at a shorter wavelength. So basically that means improved receivers.
Mm-hmm.
And number two, it's actually important to try to put a telescope with this type of detector up in orbit. If you put it up in orbit, then you improve the angular resolution a great deal, because you can have baselines that are larger than the Earth. And so it's the combination of those two things that will make it possible to see the accretion disks, the photon rings of more of these supermassive black holes. And you're absolutely right. They are going to be all over the place in terms of their orientation, in terms of the amount of spin that they have, and how much squashing we see. Yeah, they're going to be all over the place.
Right. And could you briefly say why would some black holes have these jets and others not?
That is a fantastic question. It's actually not a question that is very well understood. So these jets that we're talking about, these are my specialties. So when I told you near the end of the talk that I really was gratified to see those magnetic fields, it's because that's what I work on. I tend to work on the larger scale structure more than the smaller scale structure, but we don't have a great understanding of why it is that only about 10 or 15% of accreting black holes have jets. We believe that it has something to do with the strength of the magnetic field, but we also believe that it has to do with the type of accretion flow that it has, and there's a lot more work that needs to be done towards understanding this. I would be lying to you if I told you that it was well understood. We do understand, we think, why when we see them, they are accelerated, but that doesn't answer the question of why some objects have them and other objects don't.
Okay, thanks.
Yeah.
We had the other question from someone online.
Yes,
hope
I
I
have
didn't-
one.
Okay, great. I hope I didn't scare you away.
No, I'm back. Light coming from beyond a black hole passes it. It's outside of the event horizon, outside of the photon ring or whatever you called it, but it gets bent and we see it on Earth.
That's exactly right.
The wavelength of the light that we see, is it longer than the wavelength before it passed the black hole?
So let me move back to a plot that I showed, and I actually didn't spend any time on it, on talking about that particular aspect, but the answer is yes. And let me talk about exactly what would happen to it. Give me 1 second. Yeah, here we go. Okay, so this plot, I used it to talk about the spin of black holes. So what you're looking at here on the right is you are looking at the X-ray spectrum of the gas that is around the black hole. And I particularly want to talk about this region of the X-ray spectrum, the shaded region, and a feature that is not really visible here, but it's this feature here that looks like a very sharp peak. It's an emission line that's due to iron. It's called the iron K alpha line. The shape of that line is very sensitive to the direction of spin and how much spin there is. And it's sensitive to that because of two things. So first of all, the material that is emitting that line is orbiting the black hole. Okay, and so some of that redshift and blue shift is from the orbital velocity. In addition to that, you have special relativity. Special relativity means that the material that is orbiting in our direction has its light blue shifted. The material that is orbiting in the opposite direction has its light red shifted. And also the material that is moving in our direction is much brighter. Okay, that tends to make the core of the line a lot brighter. It makes the red wing of the line either a lot brighter or a lot fainter. And the second factor is that the closer the material is to the black hole, the more the path of the light from it is bent. This also makes the wavelength of the light a lot larger. And so you have the gravitational distortion, and this really makes the wing of the six kilovolt line a lot longer. So this is that wing that we're talking about that you can observe if your black hole is rotating either in a retrograde in a prograde fashion, and that's you can observe it particularly because in that case, the black hole can have a disk that basically goes right into the event horizon. And so you can see essentially material that has its geometry bent in just the most extreme fashion that you could imagine.
So my question is, if it was a shorter wavelength before it passed the black hole and a longer one when it gets to Earth, where did the energy go?
So it basically went into trying to overcome the distortion.
Did it heat the black hole up?
That is a great question. I don't know the answer to that.
Or is it the same number of photons? 'Cause if it is,
So
there's a longer wavelength that heated the black hole up. Conservation of energy.
yeah, I understand that. And so that's actually something I don't know the answer to that question. And this is one of those things. So black holes can be heated. So Stephen Hawking wrote a lot about this, and I suspect that you're probably thinking of a bunch of the things that he wrote about black hole entropy, possibly adding energy to black hole, but also whether black holes can dissipate. There is a lot that we think we know, but there is a lot of uncertainty about that. And part of the reason there's a lot of uncertainty is because we can't probe that region. You know what I mean? The questions that you ask are great questions, but there's a limit to what I can answer because unfortunately the speed of light puts a limit onto what we can actually probe.
Thank you.
Just talk, Mario.
Oh, thank you. Can you hear me?
Yes.
Great, thank you. Nice talk. Question I have is, I understand that the timing for the combination of the different observation sites is critical in order to get the minute-to-minute variation you talked about. But what about the large-scale structure? Would it be possible to combine observations of the entire Earth at one point with 180 degrees apart when the Earth is at the other end of its orbit and get very good large scale but very detailed resolution that way?
So in theory, you might be able to do that. But in practice, it's enormously difficult. And the reason why it's so enormously difficult is because you have to know the positions of all of your antennas from minute to minute in 3 dimensions. And so you would have to be able to track that with an accuracy of millimeters over something that is the size of the Earth's orbit. And so millimeters in accuracy over 150 million kilometers. Yeah, that's really difficult. I don't want to discourage the undertaking because I think it's a really interesting question. And like I said, the large scale structure, actually paradoxically, the way that it's probed is by smaller baselines, because a smaller baseline, to understand what it does to your resolution, basically the larger your telescope, the better your angular resolution, the smaller scale your structure, you can understand. And so for the large scale stuff, you actually want short baselines. You actually want small distances. And so that is something that is actually, that's kind of a known thing, because that is something that we had an understanding of from the observations that got done. And that is where images like the one that you see here, which was from the VLBA, came from.
Okay, thank you.
Can I get one more? Could you go back to that spin screen just for 1 second?
Yeah, just give me a sec.
Does the rotating accretion disk couple to the spin of the black hole in any way? Does it cause precession? Does it slow it down or speed it up?
So that is a really good question. And there is a phenomenon that is predicted by general relativity that we actually see at a very small scale in satellites, and it's called lens thirring precession. Lens thirring precession is produced by the bending of space-time and the fact that space-time itself around a rotating object actually rotates. And so what that means is that, let's imagine that you have an accretion disk around a black hole. That is going to precess if you have a spinning black hole. And
the black hole will precess?
and let me just finish. The precession takes the form of a warp that basically kind of makes like a wave that travels around. Okay, go.
I was going to say, does the black hole precess or does the accretion disk precess?
The accretion disk precesses. Whether the black hole precesses or not, that's actually an interesting question that I don't know the answer to. We know that there can be precession and there can be changes in the rotation of neutron stars. And we know that that is actually something that is observed. And the way that we observe it is because, neutron stars, we observe the pulsing of their radiation. That's why they're called pulsars. And one pulse is one rotation period. And over time, we see their rotation generally spinning down, slowing down. And occasionally, every once in a while, there is a glitch where their rotation changes in a relatively large amount all of a sudden. We don't know whether black holes can do that. If they can do that, that would be fascinating. But the immediate question is, how would they do that? And I don't know the answer. I don't think anybody does.
Well, yeah, the reason I was asking, it wasn't this one, it was the prograde retrograde spin of the black hole. I was wondering whether a prograde spin of the accretion disk and the black hole speeds up the black hole spin over time and a retrograde one slows it down, or how that works.
So it's not that the prograde rotation spins it up or slows it down. What happens, however, is that as matter spirals in, it does add angular momentum. And so it can make the black hole's radiations, if it's prograde and it's rotating in the same direction as the black hole, as it accretes in, it adds angular momentum in the same direction. And so that means the black hole spins up, speeds up in its rotation just a little bit.
Okay, thank you.
All right. Yeah. Think that probably be it for the night.
Okay.
I do want to thank you for a very nice presentation. And I don't think he got to hear you guys earlier because we didn't have the mic on. So what do you all think of his presentation tonight? Thank you, Eric. A lot of information there.
Well, thank you. I really appreciate your attention, and thank you so much for inviting me and listening to me.
So we'd love to find out more about astronomy.
All right. All right.
Thank you.
Well, I am going to go on home. I actually have not had dinner yet because I had a 5 o'clock class to give. And so you are catching me on fumes here.
I understand what that's like.
Thank you so
Yep,
much.
I'm sure you do. All right. Good night, everybody.
Tonight,
Very appreciated. Thank you.
Thank you.
thank you.